Welcome to solverfy.
All right, so to start off with any conjecture, one has to try out different values. And so let's just try out with the first 12 values and see what happens. Okay, so 1 to the power of 4 is 1. 2 to the power of 4 is 16. 3 to the power of 4 is 81. 4 to the power of 4 is 256. And you continue this way. 5 to the power of 4 is 625. 6 to the power of 4 is 1206, and you already start noticing that there's a lot of ones and sixes which appear. But then you continue, you see what happens. 7 to the power of 4 is 2401. 8 to the power of 4 is 4096. Again, sixes and ones. 9 to the power of 4 is 6,561, and 10 to the power of 4 is 10,000. And finally, let's just find two more. 11 to the power of 4 is 14,641, sorry. 12 to the power of 4 is 20,736. Okay. So when you look at the last digit of all these numbers, you can see there's an awful lot of ones and sixes. Okay, there's here a 5, but then we go back to 6 and 1, and then also a 0, which we shouldn't forget. You can go on and continue, but let's just start and emit the conjecture that the last number will be a 0, a 1, a 5, or a 6. Okay, so to approach this, I will start by reminding the binomial theorem, which states that x plus y to the power of n is equal to the sum, where k goes from 0 to n, of x to the power of k times y to the power of n minus k. All right, and in our case, we have x plus y to the power of 4. I mean, it's not necessary to write it down, but it clears the mind. Is equal to x to the power of 4 plus 4x cubed y plus 6x squared y squared plus 4x y cubed plus y to the power of 4. And why are we writing this down? Well, if you have a number, let's say, and you write it decimally this way, okay? By that I mean, for instance, if you have the number 5,326, this here is A1, this here is A2, this here is A3, and this here is A4, okay? So this can represent any number with n digits, okay? Well, you can always write it in this way here. 0 plus A1, okay? And that basically takes out the last digit, and we obtain these two numbers. So in this case, it would be as if I was writing this here, all right? And the idea behind this is, well, I'm thinking that this 5,320 shouldn't really matter in some sense, because as we take a power of it, then we'll always end up with something with a 0 at the end. And so if we're looking at the last digit, well, maybe it's only the last digit which matters. But this argument is a bit fuzzy, and let's try to make it a bit more rigorous, right? Well, first of all, notice that this number here is a multiple of 10, okay? So you can write it as an minus 1, blah, 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 a2 times 10, okay? And when I mean this number, it's this whole number here. And that's the most important part of it, because What happens in this case here, so let's look back at our binomial, at our formula here. What happens if x, let's say x, is a multiple of 10? So you can write, for instance, x equals 10 times n, okay? So you don't care about n is just some integer. Well, x to the power of, k is equal to 10 to the power of k times n to the power of k. But then that means that the last digit of this number will always be 0. So last, I'm going to write this, last digit of this will be 0. I mean, just take, for instance, k equal to 2, then you have 100 times n squared, which ends up with 2 zeros at the end. So in particular, the last digit will be 0. So in our case here, suppose x is a multiple of 10 and y is some number, then you notice that this number here will be ending with 0. This number here will end up with a 0, and therefore this number here will end up with a 0. And the same argument goes for here and here. And so what we've ended up showing is that the only number which matters if x is a multiple of 10, the only thing we have to look for if we're trying to look at the last digit of this is simply this here. And so when we have if we take a look back at this decomposition, well, if you have a number an minus 1, okay, so say you're looking at the fourth power of this number here, well, that is equal to an minus 1, blah, 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 a2 0, ending with 0, plus a1 to the power of 4. Okay, and this here is a multiple of 10. And so by what we have just said, the last digit of this number here is the same as the last digit of a1 to the power of 4. Okay, a1 being our y in this case. And what does this tell us? Well, it tells us that we only have to check 10 different values. A1 taking the values between 0 and 9. And actually, I didn't check the first value, which is 0 to the power of 4, which is equal to 0. And that is exactly what we've done here. Wait, I'm sorry about this whole mess. And that is exactly what we've done here. We've checked the first 10 values, and we've seen that it can only take the values 0, 1, 6, and 5. And so actually checking the first 10 values is enough to prove this conjecture, since it is always the last digit of a number which determines the last digit when taking to the power of 4. Okay, so I hope this helped. It's always a good exercise to come up with conjectures and also then trying to solve them. And the important step here is to really have this, to have this vague idea that, well, if that this part here of the number, the big part in brackets, big part here, doesn't really matter in determining the last digit. And then you have to obviously go through the rigorous phase, and that's where the binomial theorem helps quite a lot. Okay, well, I hope this helped, and have a good day.